Electron configuration in a nutshell. So what is electron configuration? What you're basically trying to do electron configuration is show all the electrons an atom has and give the location for each. It's kind of giving an address for each and every electron for an element, which sounds kind of like unnecessary, but there's actually a lot of things going on with that. So the concept of this is going to be under quantum mechanics, which in itself seems like a really scary thing. And in all reality, if we're going to deep into it and talk about the physics and the mathematical components, it is pretty daunting. But for our purposes, we're going to go over some basics. We're not going to go full force into it. So what quantum mechanics does describes the location of electrons using 4 quantum numbers that apply to its location in terms of its shell, subshell, orbital, and spin. It's kind of like someone being able to locate you based on the street number, the street, the room, and which bed you're sleeping in. I mean, if you want to go that route with it. So it's basically just giving you like a GPS location for any electron for an element. And obviously each electron has a unique location, more or less. So the first number we're going to talk about is the principal quantum number. This is just basically the shell number. So in the periodic table, if you look, you have 7 periods, right? So there's basically 7 possible principal quantum numbers, 1 through 7. Those are your options. Describes the energy level shell electron is in, with energy of electron being larger the further it is, which basically means that the further the electron is, the more energy it has. So an electron in the 7th shell is going to have more energy than the 6th shell, and the 5th shell, 4th, 3rd, 2nd, 1st. So the lowest energy electron is going to be the one in the 1st shell. That's the way you want to look at it. The further you go up, the more energy the electron has. Number of electrons in each shell is represented by 2n squared. So what the heck does this mean? So let's say I ask you, how many electrons are in the 4th shell? And you're like, I have no idea. Well, use this formula to figure it out. So the way it works is you square the number first, right? So 4 squared is 16 times 2 is 32. So the 4th shell has 32 electrons. What about the 5th shell? Well, you're going to plug in n as 5, just like we did here. So 2, put 5 squared. So 5 squared is 25 times 2 is equal to 50. So basically, you're able to locate or figure out how many total electrons an element has by using this calculation. That's all it's used for, just to give you an idea how many electrons are possible in a shell. All right, the second quantum number is called azimuthal quantum number. It's basically your subshell. Let's ignore the azimuthal quantum number for a second. Just call it the subshell. So for subshell, you have 4 different options. You have S, P, D, and F. And for those wondering what the heck does that even represent, without getting too scary with this, it's basically telling you which area your electron can be found for that element or for that set of electrons. So 1s, if you have an electron in the 1s orbital, it's somewhere in the sphere. Or if you have 2s, somewhere in this sphere. 3s, somewhere in this sphere. What if you have p? Well, p is going to be somewhere in this figure 8. And for the figure 8, whereas for the sphere you only have 1 spherical option, for the figure 8 you actually have 3 different axes, x, y, and z. Yeah, it gets kind of scary if you start talking about the different variations. We're not going to go into it. I just want you to understand that the only thing this represents is which region the electron is found in within the shell. That's all it is. And we're not going to try to memorize all this and make it really scary. But what you do need to memorize is how many orbitals each of these shells have. So S has only 1 orbital, just this circular pathway somewhere, right? P has 3 orbitals. Why 3? 1, 2, 3. D has 5, F has 7. You just have to memorize that. That's how many orbitals. And what is an orbital? Somewhere an electron can be found. So for an S, you only have 1 orbital. So that means that the electron is found somewhere in that orbital. For P, you have 3 different orbitals. So the electrons can be in any of these 3 possible locations. That's as far as we're going to go with this. The next quantum number represents the orbital itself. It tells you if it's in that 1st, 2nd, or 3rd shell, right? So when we talked about P, you have 3 different orbital options. So this next quantum number tells you which one of these orbitals you're in. For S, you only have 1 orbital, so only 1 shot. And the last quantum number is called your spin. There's really only 2 options. Either electrons can be facing up or facing down. So let's say we have 3 electrons in the subshell. So let's go an example of one. Let's say we're doing lithium, right? We want to show all the orbitals for lithium, all the possible locations. So for lithium, it turns out it has electrons in what's called the 1s and the 2s. So it has a total of 3 electrons. If you look in the periodic table, the atomic number 3 says 3 electrons. So the way the spin works, there's 2 options in each orbital. Either it's facing up or down. Your first electron's always facing up. The second electron, which will always go in the same orbital until it's fully occupied. An orbital is fully occupied when you have 2 electrons in it. So that second electron is also going to be here, but it's going to be facing down. That's what spin's referring to. Is it facing up or down? If it's facing up, it's positive 1/2. Facing down, it's negative 1/2. For here, you have one more electron. Which way does it go? Facing up, because you only have 1 electron. So it tells you if the electron has a positive spin or negative spin, and that's as far as we're going to go with that. So we have shell, subshell, orbital, and spin. Those are your 4 different possible things you need to lock into memory. We're going to talk about each one in more detail. All right, some general rules before we get to that. The spin and Pauli exclusion principle. Pauli exclusion principle basically says that no 2 electrons in an orbital can have the same spin. So what that means is that, let's say we have that 1s orbital we're talking about for lithium. You can't do this, nor can you do this. Both no-nos. That's all Pauli said. You can't have 2 electrons with the same spin in the same orbital. That's as far as we're going to go with it. All right, so some general questions. How many electrons can the principal energy level 4 hold? Well, remember how the equation works. It's 2n squared. So we go 2, 4 squared. 4 squared is 16 times 2 is 32. That's all you got to do. How many electrons can the principal energy level n equals 3 hold? Same logic, right? You go 2n squared again. So 3 squared. 3 squared is 9 times 2 is equal to 18. So there's our answer. The number of electrons in a p orbital. Well, an orbital this is not referring to a subshell. That's where it gets sneaky, right? A lot of you guys probably looked and said, oh, p subshell. There's 3 possible orbitals, and each one can hold 2, so it's 6 possible. It gets really weird. Here, it just said p orbital. So we're just talking about one of these. Any single orbital, whether it's p, d, f, or anything else, it's only going to have 2 options. It's going to have 1 electron or 2 electrons. You could also say it could have 0 electrons technically, but that's not the options, right? So the correct answer for this, it could either have 1 or 2 electrons. Number of orbitals in a p subshell, well, we've already established that. You have to memorize that. That's going to be 3 orbitals. So when you hear p, you're supposed to need 3 orbitals. Number of orbitals in a 4d subshell. Well, D has 5 orbitals. The number in front of the shell number is not what you use to figure out the number of orbitals. It's the letter. The letter tells the number of orbitals. D has 5 orbitals, so that's going to be your answer, 5 orbitals. A number of electrons in a 3D subshell. Well, D has 5 orbitals, right? So we're going to put 5 slots, 1, 2, 3, 4, 5. Each one can hold a 2 electrons, so you have a total of 10 possible as a maximum. All right, electron configuration. Used to show that where all the electrons are for an element are located. For example, 1s2, 2s1 tells you have 2 electrons are in the s subshell of that first shell, and 1 is located in the s subshell of the second shell. Probably like, what the heck is all this? When I give you electron configuration, like let's say I give you this, 1s2, 2s2, 2p6. What I'm basically telling you that there are 2 electrons in the first shell in the s subshell. One's going to obviously face up and one down, right? According to our Pauli exclusion principle rule. You also have 2 electrons in the second shell, in the S subshell. And then you have another 6 electrons in the P subshell in the second shell. So the second ring has an S and P subshell. The S can hold 2 electrons. The P can hold a total of 6 in the situation. So that's what I'm basically telling you, just how many electrons are located in each place. That's all electron configuration information gives you. This has a total of 10 electrons, and if the atom was neutral, well, 10 electrons means it has to have 10 protons, right? Neutral means equal numbers of protons and electrons. So what has atomic number 10, which is what your protons gives you? That's right, neon. All right, using periodic table to draw electron configuration. So this is going to be your best friend for electron configuration. When you need to draw electron configuration, you're going to have to use this. The way it works is we're going to go fill it from left to right. So this is hydrogen. This is helium over here, right? So hydrogen only is going to have 1s. It's going to be 1s1. Helium is going to be 1s2. This is the only time the S block is actually on the right side. If you notice, the S block is on the left side. We call it the S block because everything in these two groups end with S. The front number just tells you which period you're in. It's the D block. The D block is weird. Whereas the S block, the period number tells you, what your front number is. For D, it doesn't. Because here, we're in the fourth period, right? That's why it's 4S. But this is 3D. What the heck? All right, the D block is a little weird because this is what happens. The D is going to be one less than your period number. So this is going to be period 4. So one less than that gives you 3D. So for all these, if you notice, it's 4S, 3D. The D is one less than the period number. Whereas for the S, the period number is the number in the front. So that's the one little trick, is that this number for these is going to be one less than the period number. Let's go to the P. P can make sense again. So you can see the second shell has 2P. Third shell has 3P, 4P, 5P, 6P, 7P. So here, the P, or excuse me, the number of the period tells you what your front number is. There's no subtracting. There's nothing cute going on. Just matches up. Down here, we have the F block. Now, the F block, in case you were not aware, and you're probably not, are actually members of period 6 and 7. What happened, if you look at the atomic numbers, it makes more sense. They pulled these two periods out from period 6 and 7 to condense the periodic table and put it in one page. I know, sounds like a really weird reason, but that's what happened. The F is also weird, because look, it goes 6S, then it goes to 4F. So your F is 2 less than your period number. D is 1 less. F is 2 less. So we go 6S, and then we go to 4F. And then we go to 5D. So let's talk about how to use the periodic table to figure out what the hell is going on. So this is the way it looks. So we're going to go with an element all the way over here, fluorine. Now, this is S1, excuse me, this is P1, P2, P3, P4, P5, P6. What I'm basically showing you, this is a stop sign. This is the last electron that should be filled for this fluorine, should be P5. Why? Because that's where the last possible electron is. This is S1, this is S2, and in case you're wondering, this is D1, D2, all the way to D10. And if you are kind of catching on so far, this starts with F1 and goes all the way to F14. All right, so this is the way we're going to do electron configuration. We're just going to go left to right like we're reading a sentence. So your first electron configuration for fluorine will be 1s2, right? Go from here to here. What comes next? Left to right, 2s2. Before you can go on to the next location, you have to fill that current one. S can have a maximum of 2 electrons. So once you say 1s2 or 2s2, you're done with the S's. Now you can go on to the next one. You're going to 2p. So where do I go for 2p? 2p5. Why 2p5? Second shell, p5 is our stop sign. Now here's the way this works. Look how many electrons this has. 5 plus 2 plus 2, it gives you a total of 9. If you look at fluorine, the atomic number is 9. Since the atom is neutral, 9 protons means about 9 electrons. That's where the number came from. Let's try a different one. Let's try chlorine. Actually, let's make it a little more interesting. Let's go with, over here, we have aluminum, gallium. Actually, let's go with chlorine. That'll be easier. And then we'll go on to these weird ones in a second. We'll go to zinc after this, just to show you what it looks like. So for chlorine, same thing. It's got a total of, it stops at 3p5. That's what chlorine is, 3p5. Same thing as fluorine, except it's in the third shell instead of the second shell. That's where we end at 3p5 and not 2p5. So same thing, 1s2, 2s2, 2p6. All I'm doing is just reading across. 2s2, going to the 2p, so 2p6. Now down here, left to right, 3s2, and then we go all the way across to 3p5. Now count your exponents, 2, 4, 10, 12, 17. Guess what the atomic number for chlorine is? 17, so that's how many protons and electrons it has. We'll do one more, zinc. Zinc should end at 3d10. 10. That should be our stop sign, 3D 10. Why? Because it's 3D, right? And it ends at D10. That's why I should stop there. So we're going to go all the way, same thing, 1S2. It's the same routine, same exact sequence. It doesn't change, guys. Just a question of where you're going to stop. 2P6, 3S2, 3P6, 4S2, 4S2, right? Now comes the D's, and that becomes 3D10. Now, if you count your total numbers, 12, 18, 20, 26, 28, 30, guess what the atomic number for zinc is? You guessed it, 30. One other thing, the reason that 3D comes after 4S, because even though this is in the third shell, it has less energy than the 4S electron. Really weird, I know. Remember, the further it is from the nucleus, the more energy it has. So the fourth shell should have more energy than the third shell. But it turns out, for some strange reason, even though that the D electrons are in the third shell, they have more energy than the 4S electrons. It makes no sense, but that's the way it works. Because what you're doing when you're doing this Aufbau principle electron configuration is you're going from lowest energy to highest energy. So the lowest energy electron is the 1S here. The highest energy is the 3D10. So that's where we use the periodic table to figure it out. All right, so your first number, once again, is your main shell. Second, the letter tells you what subshell. And the exponent tells you how many electrons are there. So let's look at some of these. Hydrogen is 1s1, helium 1s2, lithium 1s2, 2s1, carbon 1s2, 2s2, 2p2. I'm just going left to right using the periodic table like I did before. And sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. Notice that the total count on the exponents matches the atomic number for sulfur, which is 16. All right, let's try some more. Chlorine we already did earlier, so I'm not going to do it again. Maybe we could do something more fun. It was boron. I messed that up. It should have been boron, aluminum, gallium. So let's do gallium. All right, so how do we do gallium? We start with 1s. So this is for gallium. We go 1s2, right, left to right. What comes after 1s2? 2s2, right, which is right here. Then we go through the 2p's, all of them, so 2p6, because we're not stopping. What we're stopping at, and you can tell right off the bat here, is going to be 4p1. So once we get to 4p1, we're going to stop because that's all the electrons we need to represent. So it comes after 2p6, 3s2, and 3p6, 4s2, and then it gets weird, right? Because your D is one less than your period number, so it should be 3d10, and then ultimately stop at 4p1. And once again, if you count your total number of electrons, you get the total of 30. Your valence electrons, one other thing I want to point out here is the electrons in the last shell. So remember, D, the 3D is actually in the third shell. So how many valence electrons does this have? Well, 2 plus 1, 3. So you have a total of 3 valence electrons. In case you were wondering how many electrons in the last shell, just look at your S and P only. That's how you can tell how many electrons are in the last shell. All right, strontium. What's my stop sign? Looks like it's going to be 5s2. So I'm going to keep on going, doing this Aufbau principle until I get to it. So for strontium, we'll go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. So I have to go fill them all up, right, before I move on to the next one. And then we have 5s2. The last one, your iodine, your stop sign, that's what you want to figure out first, is going to be 5p5, right? The p5. So I'm not going to draw this from scratch. I'll just show you what it looks like. So for iodine, there you go, all the way to 5p5, just as we predicted it. So all you're doing is just the same exact sequence, and all you need is the periodic table. You just have to remember the first two groups are the S, the middle ones are going to be your D, and they're one less than your period number, and your last one's going to be your P's. All you do is just go left to right across the periodic table, and you'll be able to do electron configurations using it. All right, orbital diagrams are like what you just saw, except instead of using exponents, we're using arrows. That's the only difference. So for lithium, which is 1s2, 2s1, instead of doing 1s2, 2s1, we draw this, the arrow notation. So first arrow, remember, is always up, second arrow is down, and then the next arrow or the next electron is facing up. This is called a filled orbital. This is called a half filled. And this is called an empty because there's nothing there. All right. Once all the orbitals in a subshell are filled with one electron, you can then place the electron with the opposite spin. So you have to have all the orbitals occupied. So what the heck does this mean in English? All right, take a look. You see for nitrogen, you have 7 electrons, right? So the first one up, so the next one down, up, down. Now look what happens in the P. You don't do this. That's a big no-no. No, we don't do that. What we do instead is we put all the electrons by themselves first, and then we pair them up later. So that's why all 3 of these are alone. So what happens if you did a down arrow and then didn't do this last one? You'd be wrong. You have to have all the orbitals occupied. So put all the ups before you put any downs. So make sure for P and D, you have all the up arrows before you put any down arrows, and F as well. All right, for oxygen, once again, notice up, up, up. And now, because oxygen has 1 more electron, there's a down arrow. That's the only reason there's a down arrow. For fluorine, same thing. Next one's a down arrow, and you guess for the last one, down arrow as well. All right, Hun rule is basically what deals with this. It says that you cannot put any electrons spin paired, or means 2 electrons in the same orbital, until all the orbitals are occupied. For S, it's really easy. You only have one orbital, so the first one's up, second one's down. For P, you have 3 orbitals. That means you have to have 3 ups before you have any down arrows. And that's what Hun's rule basically says. You can't have any down arrows until all the orbitals are occupied. So remember that. All right, diamagnetism and paramagnetism. This is basically telling you something's magnetic. So diamagnetic basically means that all the electrons are spin paired. So you're probably like, what the heck does that all mean? Well, spin paired means that, let's say we're doing this. Let's say this is P. So all these are not all spin paired. So this would not be a spin paired atom. What I mean by that is that not all the electrons are spin paired. There's one that's empty, right? It could look like that. It could look like this. It could look like this. Like any variation. The only time that it's diamagnetic, these are all paramagnetics, by the way. The only time it's diamagnetic is when it's all spin paired. So when all the electrons, all the orbitals are fully occupied, you're spin paired, then you're diamagnetic. So when is diamagnetic? At S2, D10, P6, and you might as well throw F14 in there as well. So you're like, well, why do I even care about this? Here's why. If it's paramagnetic and it's a metal, you can use a magnet to attract it. That's the whole point of it. This is why iron is magnetic, because it's paramagnetic. If you draw electric configuration for iron, you'll get 3D6. So 3D6 is not S2, D10, or P6, or F14, right? It's whatever your ending is. As a result, it's diamagnetic, so as a result, it's paramagnetic, so you can use a magnet to attract iron. You can use it on zinc, by the way. Majority of our coins are made out of zinc, so you can't go into a vending machine, put a magnet next to the, where the change is and pull the money out. You can't do it because zinc is not magnetic. So metals that are paramagnetic are generally attracted by magnets. Those that aren't. All right, so electron orbital diagrams for carbon. So for carbon, we're going to do the old-fashioned way first. So we're going to go 1s2. There's a total of 6 electrons, right? So 1s2, 2s2, 2p2. That's the old way, right? What's the orbital diagram? Up, down, up, down, up, up. So basic reference is the same thing, but this is what the orbital diagram is. You're just using arrows instead of exponents. That's the only difference. For oxygen, same thing. We have 1s2, 2s2, 2p. If you look at oxygen right here, we stop at 2p4. So let me put 2p4 down here, and then look at your orbital diagram. 2p1, 2, 3, 4. All right, magnesium, the last one. What do I do for that? 1s2, 2s2. Magnesium right here in case you can't see it. So we end up at 3s2. That's our stop sign. So we're going to keep on going until we get to 3s2. So 2p6, 3s2. And then voila. So this one is paramagnetic. This is paramagnetic. This is di. Why? Because all the electrons are spin paired. There's no electrons by themselves. They're all bunched up with another electron. All right, some concepts you need to be aware of. Ground state configuration means you're filling the electrons in order from lowest to highest. So what I've been doing all this time is ground state. Notice. Excited state means an electron is out of sequence. How the heck do you determine that? The correct number of electrons for the elements, like for nitrogen, you have a total of 7 electrons, right? So if you do excited state for nitrogen, you'll have 7 electrons. The only thing is they're out of order. Notice this is not fully occupied. This is not fully occupied, yet we have a 3s electron. That's a big no-no, right? You have to fill all these up before you get to 3s, but you're not. That's how you can tell it's excited state. Correct number of electrons, 2, 3, 6, 7, but it's out of order. And for cations, you lose electrons. So for iron, this is what it looks like for the cation. So you're probably like, okay, what's the significance? Here's what the original iron looks like. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. It's a cation. You lost 2 electrons. Guess where you lose your electrons from? The shell furthest away from the nucleus, which is your valence shell. The 4s goes away. So when you take electrons out, you're taking away from 4s before, you're taking out from the s before the d. That's the best way to look at it. So if you're doing cations, take it away from the s subshell first and then the d. If you take it from the d first, you're wrong, because you can't take it away from the 3rd shell before the 4th shell. It makes no sense. But keep an eye on that. Some anomalies, partially filled and fully filled subshells are preferred. So some strange things happen. You're like, what can be stranger than what I've just seen so far? Here's what happens. All right, chromium, right here, this whole group does something really, really weird. Now, you would think that it would be 3d5 4s1. For chromium's group, what it should be is that it should be 4s2, 3d4. How do I know that? This is d1, d2, d3, d4. Should be 4s2, 3d4, right? That's not what happens. It instead is 4s1, 3d5. Why the heck does that happen? Because this half-filled thing works. Same thing happens with molybdenum, tungsten. They all do the same thing. It's going to be s1, d5 instead of s2, d4. So be aware of that. That's the correct electron configuration. So if I give you this, 4s1, 3d5 for chromium, be like, yeah, that's the correct electron configuration. Don't worry about this. Fine, this is called a shortcut. What you're doing is you're basically banking it. We're not going to be doing the shortcut, but just so you understand why is there argon in brackets. What you're basically saying is that here's my first 18 electrons. I'm going to show it this way, and I'm going to continue from there. We're not going to do that because that's no fun. But that's what this represents in case you're looking at like, what the heck is this thing? Also happens here, by the way, for copper's group. Copper does the same bizarre thing that chromium's group does. So all these, look at it, D10, S1, D10, S. Instead of being 4s2, 3d9, which is what you expect, because this is 3d9 stop sign, that's not what happens. So just be aware of that. That's everybody in this group. There's this S1, D10 thing, which is really weird, but that's what happens. All right, the correct electron configuration for nitrogen. If you look at it, it's got 7 electrons. So this has 7, but what the heck happened to 2s? This has a total of 10. That's a no-no. So the correct answer is this. All right, the correct electron configuration for oxygen total has 8 electrons. Once again, what the heck is this? Where's the 2s? There's the 2s, 2p. That looks good. This one, what's wrong with it? 10 electrons again. That's a no-no. So the correct answer is 2. Correct electron configuration for calcium. Calcium should have a stop sign at 4s2 if you look in the periodic table. So without even doing any work, I already know the answer is the second one. That's electron configuration in a nutshell.